Hey guys, welcome to Monologues. So in today's video, we'll be verifying the Newton-Raphson method, which is used to find the inverse kinematics of a robot, for robot manipulator to be specific. So in today's video, we'll be using the UR5 robot as an example, because we have a simulation scene available in the net. So we are taking that as an example. So and the all the things that we are using over here are available in it, so you can actually refer them. Okay, so I have created a function in MATLAB to do the calculation of the Newton-Raphson method. So first we'll be going into the MATLAB and doing all the we'll be feeding all the parameters into the function, and we'll calculate the final theta, all the joint angle, joint variables of the robot, and then we'll use that joint variables in the simulation to verify that it works. So let's get started. Okay, so we have opened MATLAB right now and created a function already, and the function name is ik in body iterates, which basically means the inverse kinematics function in the body frame, and we'll be taking the output for every iteration of the Newton-Raphson method. So we'll look at the parameters that we are feeding into the function. So as you can see over here, there is a B list. So the B list basically means the screw axis vectors for every joint of the UR5, which is basically a 6-joint robot, 6 degrees of freedom, and therefore 6 screw axis vectors will be there. So the B list will be in the matrix form with every vector, which is basically every column of the matrix corresponding to the screw axis of every joint. So that's what B list is. Then we have the M matrix. So as you already know, the M matrix is the transition matrix, or the so from the origin to the body frame. So that is the when all the joint angles are at 0, the 0 state. This M is the transition from origin to the body frame at the 0 state of the robot. Then T will give the desired transition, which is the desired orientation and the location of the body, the end effector that we need. That is actually what we are the input of any IKs. So the T matrix will give the transformation from the origin to the desired frame. Then theta is 0 is the original or the initial guess that we are putting into the Newton-Raphson method. We are familiar with the Newton-Raphson method, and we use an initial guess. So that initial guess is the theta is 0. Then E omega, that is basically the angular velocity error range. Then the EV, which is the linear velocity error range. So these are the parameters that we are feeding into the function, and we expect to get outputs such as theta list, the final theta list, then the success, whether it is success or not. So if it is success, we will get a value 1. Then the table of theta. For every iteration there is a theta list, so we will form a table for every iteration, including the theta list of every iteration. So that's the function for you, the outline of the function. I'm not going into detail of the function, which it is basically used all the if you understand anything, just you could go through the code over here by pausing the video. I've just used basic MATLAB script to and converted the equation. There's nothing much in this. So okay. Okay, so let's first make the M matrix. Okay, so this is the M matrix. So this is for the general UR5 robot. This values can change according to the design of your UR5 robot. You can find documentation on how this M matrix came in the net. So I hope you will refer that. If you don't want to refer that, also fine. You don't really have to know how it came. We are just looking at the Newton-Raphson method over here. So that's the M matrix. Now we'll create the T matrix. So there you go, the T matrix. Then what else we need? We need the B list. We have created. Okay, so this is the B list. We can find documentation for all these things on the net. So I'm not going to waste your time by explaining that. So we have created the B list. We have created the M. We have created the desired T. This is the desired T. Then okay, then we are giving the theta is to 0. So how should we find the theta is 0? We'll do it by the simulation in the coppeliasim simulation software. We'll go right now and see how it proceeds. Okay, so we are in the VRAP or the coppeliasim window, and we'll try and position our end effector frame almost near to the desired T orientation that we require. So first of all, in our desired T, the px, the translation in the x direction is in minus 0.5. So the orange axis represents, this is the origin, the S frame origin. So the orange axis represents the x, green represents y, and the blue represents z. So we need this orientation to be 0.5, this origin to be 0.5, position minus 0.5 in the x direction. So we'll start the simulation. As you can see in these joint angle slides, all the reference is now 0 angles. So this is how it is in the basic 0 angles. So you can just cross reference the M matrix with this orientation, as you can see over here. So we'll try and change everything right now. Okay, so let's change our joint 1 and see where it turns. Okay, this is how the joint 1 turns. So we need our end effector frame at minus 0.5 position. So since this is a large variation, because we will be turning the entire length of the robot, we'll keep this at 0 itself for right now, and we'll check the rest. Well, joint 2 will change. How does joint 2 change? Okay, this is how joint 2 will change. Okay, so let's put joint 2 somewhere over here. Then joint 3, let's see how joint 3 will move. Okay, so this is how joint 3 will move. So we'll put joint 3 somewhere around somewhere like this. Okay, then joint 4. How does joint 4 change? Okay, like this. So that will actually change the orientation. Okay, we'll see the C3 values right now. Okay, so it's almost minus 0.5. We got the minus 0.5, almost minus 0.5 over there. And now we'll let's put joint 4 like that for now. let's see. Then joint file. How does joint file move? Okay, this is how joint file move. Let's put it over there. So we have almost achieved the this position. So we'll proceed with the orientation. The orientation we need is 0, 0, minus 1 for the x-axis, which basically means the x should go in the negative z direction, which is the downward direction. So we'll try to change that. Okay, we almost got it over there. Okay, or should I go like this? Okay, let's put it over there. Okay, then we need the orientation of y to be in the x direction, which is this direction. So we'll try and change this. Okay, so almost got it. Then what we need? Okay, then the z should be in the minus y direction, which is the direction right now. So let's see. Basically, yeah, we have almost got the t side. So we will use. Okay, then I'll change some also somewhat like this. Let's put it somewhat like this. Okay. Okay, let's see. Yeah, we are getting there. We're almost getting there. Okay, so we'll use these values as our theta is 0 values. Okay, all right. Okay, so we are back in the MATLAB, and I've typed the theta is 0 that we got from the simulation. So we'll enter that. Sorry, we'll enter that, and we've got the theta is 0 also. So almost all the values, we already have all the values. Now it's just that we have to the function. Okay, so we'll call the function. See here, I'm given the e omega value as 0.001 and ev value as 0.0001. You can see over here. Okay, so I'm gonna call the function, and let's see what will happen. Oh, okay. Sorry for the disturbance. It was just that I hadn't called all the library functions, so I added the library to the MATLAB, and now it works fine. So iteration 0. At iteration 0, we have got some fk. Iteration 1, we got some fk, not close. Iteration 2, we got some fk, not close. Iteration 3, some fk. Okay, this we got the fk cut iteration as the desired t there. Okay, we got the at what iteration did we get it? Iteration number 4. Okay, so the iteration number 4, we got the desired t. So this is the final theta list that we require. So we'll put this in our VREP scene. Wait a minute. Okay, we'll call this once more. Let's go and copy this. Copy. Starting the simulation, and here enter 6 comma separated angles. Okay, so we'll enter that values. Put a comma so to differentiate. And press enter. Okay, so we got a desired t over here, and this is how it will look. Okay, see. Okay, so the function was successful. Okay, we can close this and we'll go back to the MATLAB. So we put the initial guess as yeah, this was our initial guess. Okay, so we got the final result almost similar to that. Yeah, but the more close you are to the actual values, the number of iteration you need will be lower. So we got the final value in and 4 iterations. See, iteration number 4, the theta list is this, and the 4 kinematics with the current theta list is this matrix, which is actually the desired transformation matrix that we require, and the twist error and all are in the range, so everything is fine. And so this is the table of theta. This every row indicates the theta list of every iteration. So this is iteration number 1, 2, 3 and 4. So this is our final theta list that was required to get a desired transformation. So we just checked the Newton-Raphson method and verify that it works with the help of MATLAB to do the calculation, and with the help of simulation we have got and we have verified that the Newton-Raphson method works. So thank you, and I hope this video was helpful.